It should be recording now. Okay.
Okay. So this is going to be the last lecture for the course. Tomorrow we will have this short examination. I think we will share the actual text of the exam for you at 9:15, 9:30. It will pop up on the Teams channel. Okay, so you can take this PDF, put your answers there, and send it via email to me. There's no specific time constraint, but let's say I'm going to be available for questions in case you have any doubts or things around 10:30 to 12:30. If you want, you can send a message via. I had to postpone this a little bit because I have a talk tomorrow, so I might be available only after 10:30. But I think you should not be in troubles with that. So that's the plan. So tomorrow, 9:15, this assignment will pop up on Teams, and then you can fill it in and send it back to me via email. Okay. Just use. I will write it also on the channel, but you can use square brackets, ML sec, and then see something like exam or whatever. The important thing is that in the subject, use the square brackets with this ML sec tag. Okay. So that's for the thing. So today we have Maura Pintor. She is a PhD student in our group, working on adversarial machine learning, new attacks, techniques to debug and find attack failures. So she's very into the adversarial learning stuff. And I'm very happy that Maura is giving this practical talk to you, this practical lecture, so that you can also have a flavor of things that you can touch with your hands in Python and use some of the popular libraries for this. So with that said, today, and the stage is yours.
Thank you, Battista. So let me first of all share my screen. Okay, I have a very huge presentation for today. In fact, is only one slide. As I said already, it's going to be code today. So not much theoretical stuff, more practical, and also we're going to use some library that is commonly used for evaluating adversarial robustness and for, in general, for creating adversarial attacks. So the first hour is going to be just a notebook that it's very easy stuff, but it sets the scene for what happens next, where we are going to create we're going to reproduce what I do every time when I have to create some experiment to run for publishing a paper or for even for small tests. If I want to check something on a machine learning model, it's easier to have something already set up. So I can run it, have logging information. So for example, if there is some error, I can find a file and knowing what's being broken by the computer or the code. And then also, of course, we want to log the results so we can inspect them later. Because usually when you have these experiments, the attacks take a long time to produce the results. And you don't want to reproduce them every time you want to create a plot. It's easier to save everything and then load it back and maybe create a beautiful plot or compute the numbers that you need. So this is going to be covered today. And I would like to spend more time in the second part. But of course, if you have any question about Python or the collab, I will be available in the breaks for answering your question and helping you set up everything. But in order to have to start on the same level, I will clone the repository with you. And if you are able to follow and you have Python installed, it should be pretty much self-installable. Otherwise, you just can follow the lecture. It's also recorded, and then you can try it at home. You're probably at home. You can try it later again. So I would say let's start with the code. I can send you the link to the code in the chat. So important thing, I will try to go very slow, but if I go too fast, please stop me. I usually don't go fast, but feel free to do it. And also feel free to be interactive. If there is some question that you have, pop them during the lecture. There's no problem with that, or raise your hand, and that's it. I think Microsoft Teams also provides feedback buttons if you feel like I'm going too fast or anything. Just send a signal in some way. So I sent you the link, and we just have to clone the repository. So I'm gonna open, I usually use PyCharm, but it should work even if you have like just the folder and run Python on it. Or also, if you want, you can also open the notebook in PyCharm. Sorry, in Colab notebook. So you can use Google's GPUs for running the experiments. The only problem is that the second part is not written in a Colab, in a Python notebook, because there is a simple reason for that. I will explain it later. But usually I don't want to run my experiments in a Python notebook. On the Python notebook, what I do is debugging stuff, because the Python notebook allows to run cells, so separate parts of the code. And then if I want to change only a single part, I don't have to run all the previous stuff. I can keep in memory the variables. And this is the interactive Python version. Then for the experiments, we will use pure Python, and we'll set it up like it will be, it can be deployed on a workstation and then run with many GPUs and stuff. So for the first part, you can use Colab, and you can download this notebook here, Adversarial Evasion Attacks. I don't know how long it'll take. Okay. And you can run it on Colab. The only thing that you need is to install the SecML library. And for doing that, you should, look for install packages in Colab. And there is all the information you need. So basically, you would have to write these. And instead of matplotlib van, you should write SecML, and also with the option fullbox, because we are using an extra library attached to SecML. And this is going to install all the required libraries for running the attacks within the library fullbox wrapped with SecML. So it's very complicated stuff. I would suggest follow my lecture here. And then if you have time, you can run it in Colab. But it should be easy to follow, even from running on local. So first thing, I should get from VCS, from version control, my repository that I should have still in the copy. Okay. Then clone. And it should be pretty lightweight. I hope so. So very important stuff. Write the instructions in the code or in the README, so you can, when you go back to this repository, you know how to use it. Every time I create something for the experiments, I always write down some lines so I can reproduce the steps very quickly. Because if I take this code 6 months from now, probably I don't remember how to run it. It's easier if I have already the lines that I have to run written in my README. So here it's asking if I want a virtual environment. I would say yes, but I'll set it up in a different way. So I don't know if you do this, but I suggest to create virtual environments for every different repository. That's because a virtual environment allows to install libraries locally in a box instead of installing them in your machine as main Python library. That's why maybe we need a version of a library and it's incompatible with other libraries. In this way, we isolate everything and then nothing breaks. Otherwise, the most common problem is with matplotlib, the library for plotting stuff in Python. And that is always, every library requires a different version. So either you find the perfect version you need, or you only install the libraries that you need for the experiment and the version that you need for matplotlib. This is only an example. There is a lot of libraries that are like this. They have conflicting requirements. So I suggest create a virtual environment. I will use as base Python 3.8, but any version from 3.6 to 3.8 is fine. I don't think Fullbox is supported in 3.9, so let's stick to the usual. And then tick these, and I will have my clean virtual environment. So if something breaks, then we will know what to install, and I will update the requirements file. Okay, so these are the libraries that are already there. And now the first line in the repo says to install the required libraries. Let me open the requirements file. I hope the font is big enough. So as I said, we are going to install SecML with the Fullbox version. Let me also go to the SecML library on GitHub. So you can also find all the information about the library. So here we have a lot of information with the README, and there is the install guide. It says to install like this, but also if you go to extra components, there is all the extras that you can add. So there's PyTorch, that is a deep learning library that you probably already know if you're here. Fullbox is another interesting library that implements a lot of adversarial examples algorithm. So here, if I go to Fullbox, then attacks, there is all the attacks that are implemented in Fullbox. For example, there is, well, the projected gradient descent that we are going to use. It's here. And all the code is sorted. So if you want some information about the Fullbox library, it's all here. But we are going to use it inside the SecML because SecML wraps it and allows to use it with different components. For example, you can create a dataset from the scikit-learn code that allows to create simple datasets, for example, and then attach a PyTorch model to that, and also use a Fullbox attack. And SecML nicely wraps everything in a way that it's transparent, that you are using so many libraries that otherwise would require for the connection a lot of lines of code. So this is an advantage of using a library that wraps everything and presents only the interfaces to the user. And then, well, this is another library, Cleverance, that is not used that much for the experiments. The reason is simply that it was abandoned for a bit. Now it's going to be renewed, but for today, let's say we use Fullbox, that is the most used nowadays. And of course, SecML, because we wrap Fullbox. And TensorFlow GPU, it's needed if we have a GPU and if we have a TensorFlow model, but in this case, we are good to go. Okay, so install SecML and we have it in the requirements file. So if I run pip install requirements file, it's gonna download all the required stuff. So fullbox, and fullbox as dependency also PyTorch. So it's gonna be a long download. And then we have, this is gonna, we're gonna use it later, and it's the repository that contains pre-trained models, robust pre-trained models for PyTorch. So it's a benchmark of adversarial robustness, but we are gonna talk about it later. And then pandas that we are going to use to print the results. So these are the libraries that we need. Actually, for the notebook, we only require this. So let's open up a terminal. And it's a terminal that has, should be with the virtual environment now that I created. I don't see it. Ah, yes, it's written here. So here I would write pip. This is the keyword for adding a file, a requirement file. Maybe, I don't know if I can, okay. And then I pass in the file. And this should install all the required libraries in the environment that I'm using. This link is particularly weird because they don't have a distribution for this repository. It's just downloading from a tag in the GitHub project. The reason why they don't have a version for it is that every time someone adds a model, then they would have to release a new version of the library. But it's easier to just say, download the commit, and every time someone adds a new model, they just upload that link. It's just because it's automatic updating of the library, so they don't want to release a version every time. I hope everything's clear until now. This is downloading, so I can also answer some questions if you have them. In the meanwhile, so the README says to run the notebook first, and then later start with the other exercise. So we're gonna do exactly that. Let me open the notebook then. And I actually prefer to use it from the browser for showing you, but you can use whatever version of Jupyter notebook you have. Here it's saying there is a lot of stuff missing, and that's the reason. I mean, that's quickly explained. We are still installing the libraries. As soon as it finishes, I can open the notebook in the interpreter. Also, I have to check one thing. Because I want to present the notebook as it is slides, and I probably need another library for that. Yes. So it's not required for you. That's why I didn't add it in the requirements file. But it's just for having a nice presentation in the browser. So everything's zoom in and it's easier to show. So here it's installing a lot of stuff. Probably the most heavy stuff is PyTorch library that allows to create deep neural networks and train them and everything. We are using it just quickly today, but of course, if you're interested in machine learning, I suggest you to dive into PyTorch and also try to train your own models or use your own data, etc. Okay, it has collected all the packages. Now it's installing. Okay, now we have everything. This thing should be updating, and then I also want to add these. And also we have to install the Jupyter notebook. I think it's here. So otherwise pip install, and then there's Jupyter Lab. That is the library for the Jupyter notebook, if you don't have it already. Anyway, yeah, I think I should do that. Oh no, okay, it's indexing. So it's scanning all the packages that I installed, and then we can start. Also, while this thing is indexing, I can show you another interesting part of the library, that is the tutorials. So here there is 15 notebooks that explain how to run adversarial attacks in different frameworks with SecML library. So for example, if I want to create, let's say, no, wait, actually, I want an adversarial part, because I think this is only training that, well, let's see. So here you can also open in Colab, and you have all the code for running attacks on the MNIST dataset, the famous digits. And it's all written here. So if you want the tutorial stuff, just go either in the tutorial tab, in the tutorial folder, in the repository, or you can also go in the website here.
Sorry, is
Yes?
it normal that it says SecML fullbox is not compatible with the SecML 0.13? Because I'm getting that warning.
Are you using Windows, maybe?
No, I'm on Mac.
Okay, then it's not normal.
Okay.
But did you install Fullbox first?
I only give the command on the terminal pip install requirements.txt. Yes.
Okay, then it's weird.
And I'm on a virtual environment, so it is empty. It was empty.
Is it Python 3.9?
8.
Okay. Then it's weird. Yes. What is the actual error message? It says only it's not compatible.
No, initially it was a warning. SecML 0.13 does not provide the extra full box. And then it gives me an error, a true error, command error doubt with exit status. PKG config is not installed. The matplotlib may not be able to find some of its dependencies.
Okay. I'm just checking if I had the same problem and maybe it skipped it. Okay, I see these. I mean, my version did install correctly, so I don't know.
Yeah, I can try. Maybe I can try creating a new environment and see what it does.
Yes, that might be good.
Maybe instead of a virtual one, I can create. A stable one.
Yes. Otherwise, either you can try to open it on Colab.
Okay.
Let me actually check. So I think I also saw in one of the notebooks. So, for example, here. So this is the line that should be used. Oh, actually, I think I should have added this. I can send you the link, so maybe it's easier to copy and paste.
Okay.
And you should go to Colab and then install everything there. Otherwise, the other problem that I might see is that here we have SecML 0.14. Let me actually check if it's available for Python 3.8. I guess it is, because I have already used it, but it's not written here.
Yeah, Maura, my suggestion is that you keep going and then you try to solve this during the break. Otherwise, you take it.
Yeah,
off.
yeah,
Yes.
I can keep trying to solve by myself. Okay, yeah.
I was just also giving time to the others because maybe they have.
Yeah, but then it's good. If it's a problem, Giuseppe, if you can report it, then if it's a bug, we will fix it. So that would be helpful.
Yeah,
Thank
okay,
you.
now, yeah, okay, fine.
Yes, it's also, we are using you students for testing the library, so
yeah,
that's always useful. Okay, I see. There is still a problem with my interpreter. I should install PyTorch. I don't know why it didn't. Okay, then I broke also my library. Okay, didn't have PyTorch. I don't know why. So we are going to need PyTorch because we are going to use a neural network for creating a simple model. Then we can break it. After we train it, we're going to create small adversarial examples that cause a misclassification in the model. So we have a data set, then we take some point from the testing set, perturb them, and then we are going to see the label that changes from one class, the true class, to the other class. Actually, here we have 5 classes, so it's going to be very easy to misclassify. There is a lot of space to move these points. Let me check if it's installed. Okay, now I have PyTorch. And I can start the presentation. Then let's see if there is some problem. So again, we are going to create a fully connected neural network. That is a simple structure that has these layers that take the inputs, and then they are linear layers. They produce an output for each of the nodes we add in the first layer, and then pass it through other layers through an activation function. I think there is a figure later for that. So first of all, imports. If this works, then we can go on with the, okay. I should install also Torch Vision. Let me also add it to the requirements file. Okay, it's there. Then there is still some error. Let me check if I can. I think the package manager is not taking the options. Yes, so sorry for that. We are going to have to install separately Torch Vision, and Fullbox, and then I'm going to open an issue on the SecML library repository to fix this. So anyway, if you are following with the exercise, please install on separate on a separate line these 3 libraries. Also, Giuseppe, this might be the problem that you faced. I don't know. Anyway, we should be good to go now. Because in the SecML library, there is a check that if it doesn't find Fullbox installed, then it doesn't import all the Fullbox extras. So we have to have it installed. Let's see now. Not yet. Let's do plan B, and then I fix the exercise for you later, but I can use another interpreter that I know works. Let's see if this time it goes okay.
Yeah, but now I simply switched to Colab because it was simpler.
Yes, okay. Let's see. Otherwise, I will also switch to Colab. Okay. Moment of truth. It's still. I think it went okay, but. Okay, yes. It's just running automatically the notebook, so I have the outputs. So we can start with the lesson now. Okay, the imports. I divided the imports in a way that it's easy to understand what every import is doing. First, we have everything related to the model, then everything related to the preprocessing and the data. So as I said, we are going to use a simple dataset here, actually a 2-dimensional dataset. So we have, it's easy to visualize. So we can plot it into the planes and visualize everything. Then here is the code related to the adversarial attacks and the visualization part. So this should be already going. Then dataset creation. So for this, as I said, 2 features. And then we have numbers for the number of points that we want to use. And here is I'm placing the clusters of Gaussian dataset that I'm going to create in specific places. That's why we want a problem that is easy to visualize and also very interesting to cover in this tutorial. And then standard deviation. So I'm good. What's happening? Overwrite. So I'm going to create 5 Gaussians, points from 5 different Gaussians from 5 different classes. And they are going to be centered in these places. And they are going to have the standard deviation of 0.1. Of course, since usually it's a common practice to normalize everything, to standardize the input range and all the feature ranges in the data set, we're going to use a normalizer for that. So we created the data set with this instruction. And I mean, this is all the variables that we defined. If I want to change something, I mean, I encourage you to try different values for these, etc. Then we have to divide the data. As usual machine learning stuff, we divide the data set that we have in training set and testing set. The training set is going to be used for tuning the model and learning the patterns that are presented in the data. And then the testing set, we're going to use it for 2 things. One is check the model's performance, and then we are going to perturb them so that we can also measure the model's performance in adversarial conditions. So here I've put a little number for the testing set. Usually it's you divide 80 points to 20, 8 to 2. Anyways, you can put the numbers that you choose. I'm just using a small number here because I want also to run the attacks on this. And for the sake of time, I just reduce the number of points. But you can change it later. And usually in the experiments, we have bigger numbers. Then the splitter is going to divide the dataset in the 2 different datasets that we need. And here we have the normalizing part, where so this normalizer is exactly as the one that is used in scikit-learn, for example, where we have to fit it. But here it's not learning a complex model. It's just rescaling the features and taking the minimum value and the maximum value as the feature bounds. The reason why we use this fit method here is because then if we pass a different data that is very much outside of the feature bounds and we normalize it, we don't want to change the feature bounds because the feature bounds are learned from the training data. If we pass an outlier then for testing data, that outlier will be proportionally rescaled, but it still has to be an outlier, okay? So this is why we use the fit transfer and transform here. Remember this, that this transformer is doing, it's rescaling the features in the 0-1 interval, okay? This is important because then when we want to change the point, so create an adversarial example, we want this point to remain within the feature space. So we are going to impose a constraint on the attack in a way that the point doesn't go off. This is not important in this 2D case, but for example, if we have an image, we know how images are encoded in computers. They have integer values. Every pixel is an integer value or 3 integers, depending on how many channels the image has. If it's a colored image, for example, we have 3 channels. And for example, the channel red has values between 0 and 255. I don't want the pixel to go outside this range because otherwise, first of all, it's difficult to visualize. And so maybe someone that opens the image checks and they say, no, this image is perturbed because the features are outside. Or the model itself gives an error. Or simply it's ugly to see, or maybe it's not sensitive to the model because it's considered an outlier. So for this reason, we are gonna impose to the features to remain in the feature space. And if we use this normalizer before, then it's easy to do because we set 0 and 1 as lower and upper bound for each feature. And then we have this metric here that is normal standard accuracy. So we can pass here the testing set, the predictions for the testing set and the labels. And this function here gives me a number between 0 and 1, and it's how many of the labels are correct. The average, of course, in the whole dataset. And we are going to use it also for checking, after I perturb the samples, what is the accuracy then? So this is going to be used a lot in this exercise. So let's start by creating a model. And for creating a model, we use PyTorch, and we define a simple neural network. So as I said, we have an input layer and an output layer. Okay. Here, the number of dimensions is decided by the problem. So the input layer is how many features do we have in the input. And in this case, as I said, it's 2, because we have 2 dimensions. The output layer is the number of classes that we have, because for every class, we are going to have a score. And we take the maximum, and then that is the classification label. But it's like having 5 different classifiers in the end. So 1 for each of the classes. And then in between them, we can set up as many as we want hidden layers that are simple linear classifiers. And between one layer and the other, there is an activation function. So for example, it's kind of reproducing what we have in our brain, that are the neurons that fire only when there is a positive signal, and then they fire. So this is what the activation function does. Anyway, this is machine learning stuff. So I hope to have given a little background, but if you need more information, there is a lot of documentation in PyTorch library, and also pretty good tutorials on that. So feel free, and also I encourage you to try them. Anyways, this is the PyTorch code, and this is PyTorch, not SecML yet. The PyTorch code for creating the model that we want. So we create a class, and then we define what are the layers. So the layers are fully connected 1 and fully connected 2. And it's a very simple model. It has only 1 input layer, 1 hidden, and 1 output. The input layer takes the number of features. So it's the first layer is 2 neurons. Then we have in the following a number that is parametric. And it's connected to the same thing. And then we have as output the number of classes. This is how PyTorch defines the neural networks, and also every other library, they define the connections between the layer actually. And then we define also the forward function, that is what is producing the output. So it takes as input the sample, it passes it through the first layer, activation function, that is going to be the ReLU. The ReLU is just, let me use the whiteboard here. ReLU is this thing. So we have, if this is the value of the input, the f of x, and this is x. So if the value of the input is positive, it returns the same thing. If the value of the input is negative, so it should, if we continue this, it should be here. If the value is negative, it returns 0. So it's piecewise linear. But this is, again, still machine learning stuff. It's just since the attacks make assumptions on the linearity of the models, I'm showing you that inside this model, there is something that is linear because we don't want anything to be nonlinear. But it's usually said that neural networks are piecewise linear because as soon as one of the neurons changes their mind, so it, for example, it activates because the input becomes slightly positive, then the output is going to change. Let's go back to the notebook. So defining the neural network, this is standard PyTorch code that you can find in every tutorial. And we create it. This is instantiating the class that we defined. And this is still PyTorch stuff. The criterion is the loss that we use for training the model. So we want the loss to encode the fact that the accuracy has to increase while I'm training. And for this, since the accuracy is not a convex function, then we define a convex function to optimize on. And then we have the optimizer that is performs standard gradient descent. Keep in mind that you can also create adversarial attacks with PyTorch. There is also a tutorial on the website. And you can still use the optimizer because in this optimizer, you can tell it what to optimize for. In this case, we are passing the parameters of the network because we want to change them. So it's going to compute the gradient with respect to the parameters of the network and then update them to increase the loss, reduce the loss in this case. But you can do the same with an optimizer that changes the input. You just have to pass the input here. Okay? If you're interested, there is a tutorial on the PyTorch website for creating adversarial attacks with PyTorch. And there is also a library that implements all the adversarial attacks with pure PyTorch. Okay, then this is finally the code for wrapping the network within the SecML library. So we pass the network, the criterion, and optimizer. These are only required if we want to fit the neural network within the library. Otherwise, we can have the training code outside. That is a lot of stuff because when you write in PyTorch, you have to, compute the gradients, update them, update the step size and everything. You have to implement gradient descent. In SecML, it's already implemented, so it's easier to show you this. Otherwise, I could avoid to pass these parameters and just pass the model saying that it is pre-trained. And this is going to be done in the second part of the tutorial. Then we pass the input shape. This is because SecML has some transformation that standardizes also the shape of the inputs. And then we want to go back to the original inputs shape after we perturb everything, etc. But this is a long story. Anyway, we just have to pass the number of features here. So it's the input shape of the network, and it's going to be used for connecting the data that we pass to the PyTorch model. And the random state, if it's just for reproducibility. Okay, so we already run this. Then training the model, as I said, you can write your own loop, but we are going to use the easiest way, that is using SecML with the fit method. And so it's just classifier.fit, and we pass the training data and the training labels. And then after that, we can compute what is the accuracy. And so we predict the testing data and pass the true labels so they can be compared. And this should print the accuracy of the model. Hopefully. Yes, 100%. I did not expect that high accuracy, but that's fine. We're gonna break it anyways. Now, this was not adversarial at all. Was just to create the data set and the model, and then prepare everything for the adversarial attacks. Now we're going to take one point and change it in a way that it changes to the other class. You probably remember the lesson about the adversarial attacks, but I'll just refresh your memory here because it's important to understand what is the underlying mechanism behind these attacks. So we are going to use the PGD attack, that is projected gradient descent. And this is the most commonly used attack for creating adversarial examples because it's pretty straightforward. So we have this loss function that is the same function that we use for training. And instead of reducing that is the thing we do for training, no? You want to reduce the loss in a way that the accuracy goes up. Now we want to increment it. So the accuracy goes down instead. And we do that during training. We fix the images, or the samples, the input data in general, and we update the model's weight. In this case, we are doing the opposite. So we are fixing the model weights and changing the input. So we can compute the gradients with respect to the input. So because it's a function that has these parameters, the inputs parameters and the weights, we just compute the gradients with respect to the input. So we know how much and in what direction to change the inputs in order to have an increase in the loss. Also, I want to mention that there is two kinds of attacks. So the targeted attack, so let's scribble here. If I have the input space and there is, for example, 3 classes, this is class 1, class 2, and class 3. It's not writing, okay. Then I have an input sample here. No, it's outside the feature space. I have an input space here, input sample here. Then what I want to do, well, if I have an error generic attack, I don't care where the sample goes. I just care that it changes the prediction. So it can go here or here, depending on what is my constraint and what is closer, of course, and what is the gradient in that point. Now, if I want a targeted attack instead, so this is well, let's create maybe a copy of this. So this is untargeted, meaning that any misclassification is possible as long as the point is misclassified. Instead, if I want the point to be misclassified into a particular class, for example, I want the class omega-3, then I have to point to that class, no matter what, okay? I want the point to be misclassified as omega-3, as class 3. Okay, this is targeted. In this case, I think I set up everything for running an untargeted attack. That's because it's easier. Of course, as you can figure out, depending on the problem, but also in general, if I want to point to a specific class, it's more difficult than just going in a direction that causes a misclassification, because that is a bigger set. I can go in more directions in that case. And also, sometimes, though, the misclassification is actually required. So the targeted misclassification is actually required. Let's say there is a face recognition system that lets only some user enter a room. If I am an attacker and I want to go inside the room, then I have to be misclassified as that user, okay? So that's the distinction. And depending on the application, I have to check what is the threat model that I want to define for evaluating how robust is my model to that. If I have a face recognition system, probably, and the case is the one that I just described, I probably want to check on the specific classes that I want to protect. But this is a very complicated aspect of designing, and usually it's specifically required by the application who requires the application. So I'm not going into detail on that, but just for you to know that there is a version of attacks that is also called the targeted, and it goes to a different class. But today we are doing just standard misclassification. Okay, and we are going to use the projected gradient descent attack, specifically the implementation that can be found in Fullbox. We also have our version of the projected gradient descent, but I also want to expose you to Fullbox, because maybe, I don't know, for your own projects, you want to use a different library, and then you have also that code available. Actually, let me open, because I put a link in there, and we can see what is the implementation of projected gradient descent. So there is a bunch of steps, and for each step, we compute the gradient. Be aware that it's taking the gradient of the loss function with respect to the input x. What is the input x? Is the x in that step, okay? So if I have a bunch of iterations, I am trying to descend, or actually to increase the loss. As I said, we want to increase the cross entropy loss. And we are here. What I do is with PGD, or with any gradient-based attack, I compute the gradient here, and the gradient points to that direction, meaning that if I change the input in that direction, then the loss will increase of a certain amount. And then at the next iteration, I'm here. Okay, then what I have to do is, if I want to keep going, then I compute the gradient in here and make another step until I reach the maximum. And then at the maximum, I can decide, because maybe there is a slope and then the gradient doesn't point anymore in that direction, or maybe there is more to go and I don't know. And for this, we are going to explore it a little later in the debugging part. Okay, it's almost over for the notebook. I mean, at least let's instantiate the attack and run it, and then we take a 10 minutes break. Here it's just explaining the steps. Sorry, I did not finish to explain. So first thing, take the gradient. Then I have to normalize it. This is actually the implementation of the PGD algorithm that defines this normalization step. So keep in mind that we are not applying the gradient that I draw directly, but we are normalizing to a unit norm. So to be Euclidean norm equal to 1. And then, or actually the norm where that is used in the sense. Anyway, unit norm, and then we multiplied for a fixed step. And this is just because then I can tune the step without knowing what is the norm of the gradients. It's just easier to tune if this part doesn't change, okay? So we have this gradient step sign that is this defines if I want to increase or decrease the loss. And this line is updating the current iterate of x with the step size times gradients. Okay, so it's computing that little step that I showed. And then we have the projection, because the PGD attack implements a search inside a fixed ball of radius epsilon. So here, what it does, it's going maybe outside for the step, and then it's projected back so it can walk on the constraint. This is because I want to check the robustness inside that ball. This is how we define the robustness usually. So we are going to have this projection step. And finally, the last one, you see this model bounds. It's exactly what I explained before. So we have that range that goes from 0 to 1. I want the sample to be inside that. If it goes outside, I'm just clipping. So for each feature, if I have, for example, one feature that is going to 0.1, then I clip it and it comes back to 1. Sorry, I said, sorry. If it's 1.1, then it goes back to 1. Okay, it's just clipping. And here is a visualization of the algorithm. So the gray point is the initial point, so x0. And xi, so the iteration I, is the black point. For each iteration, we have, first of all, to compute the gradient. And the gradient points, for example, in this direction here. Then what I do is normalize because of the step thing that I described. And this circle, I don't know if you can see it, maybe I can zoom in a little. This circle here is the epsilon constraint. So we want to search for adversarial examples inside this constraint here. Doesn't matter if I'm in the border or I'm inside. The only thing that matters is that I don't have to go outside that boundary. Okay, so the normal step would update the point here, but what instead we have to do is project back. And the projection in the L2 norm is done like this. We create the segment that connects the point to the center, and then we place the point in the radius that is just in the epsilon constraint. Okay, and this is the iteration. Then we have to apply the input space constraint. So let's say this is the updated point that I would like to have, but since the features are in 0 and 1, and this is, for example, can be the feature range. Of course, the function, the cross-interval function, I can define it outside. I mean, it can go to plus infinity, doesn't matter. But my point can travel only inside this square here. And so I have to clip it. So every feature that goes outside, I just set it to the boundary that I have. Okay. Of course, the horizontal feature, it's not exceeded here. So I don't clip that one. I just clip the ones that are outside. So feature-wise, I have to take every feature, and if they are outside, I bring them back. Instead, in this case, we are moving the point in a direction that is Euclidean direction. That is because of the projection that we have in L2 norm. Okay. Then, yeah, we have the attack. I would say let's wait here. I'll just leave this picture so you can maybe reflect on that. And I'm setting a timer for 10 minutes from now, but of course I'm available if you have questions or you want to solve problems. And I'm also trying to solve the problem with my interpreter. Okay, 10 minutes from now, it will be 16, yeah, 4:18, and see you back in 10 minutes. Okay, we're back. So we saw what is the PGD attack. Just a quick thing, it's not easy to debug PGD attack in the version that that I showed you in Fullbox. That's also another reason why we're using the wrapped SecML version, because then, so for example, Fullbox, as you saw, it does only create the attack and run it, but doesn't log, for example, what is the value of the loss at each iteration, or doesn't log how much computation did I take, etc. These can easily be tracked by SecML library. Okay, so that's also another reason why we are using that. And we are gonna see the effect of that very soon when we visualize the actual optimization path of the adversarial example. So here we have a sample we selected from the testing set. I just took a random index. You can choose whatever point you want. And we are selecting a random target, okay? It's not actually random. It goes in the direction that increases the loss and goes in the direction that first changes the classification output. Okay, then we have 20 steps. This is very small for other applications. The number of steps depends on the application. This optimization landscape, it's very simple. It has only few classes and it's only 2 features. So it's very easy to optimize. But if I have, for example, an image from a dataset that is not even that big, the one that we are using later, so that dataset has 32 by 32 by 3 images. And that means that my data is going to be 3,000 dimensions. So in this case, 20 steps might not be enough. Also, it depends on how big is the step size of the attack. So number of steps is the number of iteration that we take. Step size is how big are each update on the perturbed sample. And then we have the maximum distance that we want to travel. In this case, we are selecting an L2 perturbation model. Of course, this depends on the application. So if I want to understand what is the robustness, if I change all the features, but the point moves only 0.3 from my original point, I use the Euclidean distance. So Euclidean distance, I hope you're familiar with math. Let's recap a little. So Euclidean distance, if I have this point A and this point B, the Euclidean distance is just the Pythagoras theorem on these 2 points. So it's going to be, if this is, I don't know, small a and small b, this is just the root square of a squared plus b squared. Okay, this is for 2 features. If I have more features, it's the sum of all the squared values and then under square root. In general, it's the distance from one point to the other, direct. So if I have a constraint in L2, what I'm ending up with is this thing. It's a circle, okay? So I have a radius. I can travel in every direction. The important thing is that I don't move further than epsilon from the original sample, okay? Let's do a quick recap on the LP norms. So there is L0, L1, L2, and L infinity. Actually, L0 means that I can change every feature of any amount. Okay, so the only thing that matters is the number of features that I perturb. Okay, so the L0 norm is just the sum of the features that are different from 0 in the perturbation. So if I have, for example, a number that is perturbed, then I don't know, this is a 7. I want to compute a perturbation in L0 norm. It's going to be just a pixel, for example, or a few pixels if I don't reach it within a pixel. Okay, this is the L0 norm. L0 perturbations are extremely sparse. Then L1, the L1 norm, again, let's recap. If I have A and B, this is also called Manhattan distance, because if we live in Manhattan, then all the streets are perpendicular to each other, or I mean, almost all of them. And if I have a building here, what is the distance that I have to walk? Well, it's this part here plus this part here. So the L1 distance is the sum of the absolute values. Actually, no. Let's write it. So it's the sum of the absolute values of the segments. Okay. This translates into a constraint if, of course, these are feature x1 and x2. Okay. So if I change only one feature, then I have an L0 norm of 1. If I change both, I can move in all the space that I designed. Okay. Because if I change both, I'm moving in every direction that I want. Okay, L1. So first of all, it's something that tries to constrain the perturbation to be sparse again. And the shape of the L1 constraint is this one, meaning that the sum of the components can only be equal to epsilon. Okay, so if this is the epsilon constraint, let's start with the easy case. If I perturb only x1, I can move it up to epsilon. Okay, so this part here, this radius is epsilon. Okay, and the sum x1 plus x2 is epsilon. If I move slightly in this direction here, so I increase also a little bit the x2, the sum of the two can only be up to epsilon. So I have to reduce, if I'm moving upwards in this direction, I have to reduce this value in the exact cutoff between the two features, okay? So if I have, for example, an update that divides in the two features half and half, I will have here exactly half and half, 0.5 per epsilon times epsilon and 0.5 times epsilon. This is another interesting constraint, and actually makes the perturbation still be kind of sparse. So the usual case here is that I will have a perturbation that is either here, 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 or here. Or more rarely, it's going to be in the exact diagonal. This is because usually the landscape is linear, so the maximum that I usually find it in the vertices of this stuff. Okay, then we have the L2 constraint that is very easy. It's just a circle. As I said, I can move up to epsilon in every direction. Can be this one, can be this one. The important thing is that I move only in a radius that is exactly epsilon. So I connect the point where I am to the original point, and if it's less than epsilon, I'm okay. An infinity constraint is more interesting. This is a box. Of course, in the L2 case, it doesn't matter if it's sparse or not, because I can go perturb both features or perturb only one. If I'm in a multi-dimensional space, it doesn't matter anymore the direction the sparse direction. In this case, if I go to the vertices, I have some probability that is higher that the solution is going to be in the vertices, and that's why L1 perturbations are still somehow sparse. In the L infinity case, the only thing that matters is the distance, is the magnitude of each feature. So this is the epsilon radius, and I can move any feature up to epsilon in plus or negative sign, meaning that for this feature, for this feature here, from 0 to epsilon, for this feature here, for 0 to epsilon. So I can reach also this point, and I'm still within the constraints, okay? In this case, for example, it's not independent if I change one feature or the other. In this case, it's completely independent. So I can perturb a lot the sample staying within the constraints. Okay, and this is the L infinity constraint, and produces the most dense perturbations because every feature can be changed and can be changed up to epsilon. So this is a lot of perturbation. If I have, for example, an image and I set an epsilon value to 1, I can change every pixel of the image. And so I can also create a different image. So in this case, of course, I expect, if I set a constraint that large, I expect to have 0 accuracy on the samples. Otherwise, there is some problem because I can completely change an image. And if it's a cat, I can turn it into an elephant. And if the accuracy is still high, meaning that the model still recognizes as a cat, there is a problem. Okay, let's go back to the code. So here we are using an L2 attack. So the circle that is centered in x0. And we can move the sample up to a radius of 0.3. Other things, so the lower and upper bound, I'm setting them to the minimum and maximum of the samples, but spoiler, it's 0 and 1 because I used the min-max scaler that's as default defines these bounds. And the number of steps. Also, there is this parameter that might be moved outside. Anyway, this parameter is the step size. So how big is the step that I'm computing? So if I want to reach 0.3 and I make steps of 0.1, it's going to be reached pretty quickly. Okay, it's not in exactly 3 iterations because it might be moving in some different direction. And also, as soon as it reaches the constraint, then it can walk on the constraint still to maximize the loss within the region that we are choosing. And I've set random start to false, but what random start does is instead of starting from the original point, it can start from a random point within the region because it doesn't matter. The only thing that matters is if I find the adversarial example inside of that. Okay, and then we are printing out some information. So we know what is the original label and the label after the attack. Let's see. Okay, it was pretty quick. With 2 features, it's just very easy. So the original label was 3, and then it was changed to 0. Now there is more interesting stuff because we want to plot. So again, it's 2 features. So as I also plotted here with 2 features, we can also plot the loss that we are optimizing and also the point and where it's moving. So it's very easy to do with SecML. Again, this was a library developed also to be helpful for a learner that wants to try and run create adversarial examples, understand what's happening, what's going on. This is very easy to do here, and also in the tutorials that are in the website. So this is just stuff for the Jupyter notebooks. And then we created this special figure that we have in SACML. It's a wrapper of matplotlib, as you can imagine. And we create a constraint. This takes care of creating a grid and then checking for every point in the grid if the system has to draw the constraint. It will be more clear in a minute. Then we plot the function that is the objective function of the attack. So it should have minima or maxima, depending on how we define the loss function. The optima point should be in the other regions. So one should be for sure in the region where I'm starting, and then the loss landscape should decrease or increase. I don't remember if it's defined to be increasing or decreasing. Let's fix it. So I want to increase the loss. So there's going to be a minimum where I start and a maximum where I end up. Then the decision regions is plotting the boundaries between the classes. This is useful because we want to know when we cross the line. Exactly that. Okay, then this is just because we want to add the initial point to the path, because the path is saved by the library whenever the model is queried. But at the first iteration, we don't try to classify the point. Because of course, PGD attack is done in this way. I compute the gradients, but I want to also know if I'm already reaching the adversarial class. So every time when I compute the gradients, I will run a query to the model, and SACML tracks it and keeps it. But in the first iteration, unfortunately, it doesn't track it, so we have to add it just for visualization purpose. Then we plot the path that is done with this convenient function and the constraint. So what we are going to see is a function that the decision function, first of all, the loss function of the attack. So it's going to be the background. Then we are going to see the limits of the classes and the original point and the point after it's been perturbed and the path that it took for that. Let's see if it works. And again, it's an error generic evasion attack, meaning that I want to reach whatever class I reach. The important thing is that it is another class, not the original class. So if it's a face recognizer, I'm the criminal and I don't want to be recognized. So I just run and go to a different class. Here it is. So the loss landscape, as I said, it has a minimum here, red. So it's minimum. Actually, no, it's actually a maximum in this case. Anyway, it has the maximum here, and the minimum is actually the farthest point from it. But we have this epsilon constraint that bounds us. So what the attack does is going in the direction that descends the most. And then here, it would like to go in this direction. But what it does is project. So it first updates, then projects back in epsilon, then updates, projects back. So it's walking in the boundary. It's doing this thing. I want to point out something here. So if we have the epsilon constraint, this thing is lagging a bit. Okay, I have the epsilon constraint, and my point is doing this. So I start here, for example, and the gradient has to go here. Then we go here. the gradient has to go here. What we can do, if the original point is here, the point is updating here, and then we trace a radius and we bring it back here. Then again, I compute the gradient, trace a radius, go back here. And so it works in this direction here. Okay, and this is the rough path that PGD does. So I want to stay inside the region, but I also want to explore the boundary of the region. Because usually, maybe if the minimum is here, then I at least reach the point that is closest to the minimum. Now, another important aspect, the algorithm that I showed you, it's not perfect. So let's say that I have, so in this case, it was the epsilon constraint. Let's use another board. If I have, this is the decision boundary. Okay. If for some reason the loss that I'm optimizing is very noisy, then I might get a path that is like this. And I don't know, at the last iteration, I compute the gradient here, but since it's noisy, meaning that the model maybe, since they were trying to defend it against adversarial examples, they tried to break the gradient descent. You've seen this in the lessons about the adversarial examples. So I just add some noise in the computation of the gradient, and that's it. So if my point ends up here in the last iteration, this is what's being returned by the attack. Okay, so the attack returns fail. But fail doesn't mean that there is no adversarial example in the region, because maybe my constraint was this. And there is adversarial examples in this region. I just don't remember them because the algorithm returns only the last one. So this is what we are trying to point out in the adversarial robustness field, that sometimes these attacks are not easy to debug. It's not easy to understand what happened, why this failed. And so this is a publication that we are still working on, but there is a preprint available. I can also show it later. We are trying to point out what are the problems with this kind of optimization stuff. Okay. So this was just to introduce the paper that I will show later. But for now, just keep in mind what PGD does, and also keep in mind that as long as the iterations are not over, PGD can still explore. In this case, I don't think it would move more. If I put 100, it will stay like this, because the gradients will keep pointing in a direction of the radius. At some point, it reaches stability because the radius is the same direction of the gradient, and then as I can update and it goes back in the same point. And of course, I'm gonna see the loss that is not decreasing anymore if I do this. Finally, this notebook took longer than I thought, but it's still fine. We have plenty of time for the other exercise. So finally, if I want to understand on average what is the robustness of my model, I have to define something that takes every radius that I want to check and creates adversarial examples within it, and then takes a slightly smaller or bigger radius, and again, check this stuff. I would have to write a long for loop for that, but instead there is a function that is already available in SecML that is the security evaluation. It's actually a class, not a function. So what I have to pass here is, first of all, the attack already instantiated. So the PGD attack that we already defined, and the name of the parameter that I want to change. In this case, I want to try different radius for the value of epsilon. Okay, and I pass a range of values that goes this is an arrange function. It's just with the fancy array that we have in the SecML library. Anyway, it's a range function. So it starts from 0, goes to 0.5 with a small step of 0.05. So it's going to be 10 values, probably. I don't know if the extreme are included, so it's going to be trial and error. Anyway, this is what we have to do. So we just pass the data to this instantiated object. And then it computes all the security evaluations. So for each point, it creates the attack, runs it, stores the results. Then it takes a different point and does it again for all the 40 points that we have. Once that is finished, it will increase the steps, the constraint in all these values and check until the end. Be aware that if we put 0 for epsilon, we are not perturbing at all the sample. So it's the original accuracy that we are going to see in the beginning. And then as long as we go up with the radius, we are going to see the robust accuracy go down until it reaches 0, meaning that no sample is classified with the original label anymore. Okay, and I mean, this is just stuff for the plotting. It's just more keywords. You can find all in the documentation. And let's start it. In the meanwhile, if you have questions, I can answer to that. Also, we are not using GPU here because there's no need for it. Probably in the Colab, you can set up a GPU, but it's not required for this exercise. I just set it up to be low computational cost. But then as you write everything, you can see it's very easy to transfer to GPUs then, because also all these libraries, they implement a very nice connector that makes almost transparent the use of GPUs. And GPUs are useful because also in the adversarial case, but generally in the deep learning stuff, because they compute very quickly the floating point operations. And also they compute, imagine having to create a graphical image of thousands of pixels. What you want to do is compute them all in parallel. And so GPUs are optimized for this parallel computation and also floating point operations that are the most used in PyTorch and in deep learning libraries. Okay, we have our security evaluation curve. And as I said, so we start from 100% accuracy, that is 1. So the average predicted label is equal. So on average, sorry, the predicted labels are all equal to the true labels. As we increase the perturbation, so the radius, we find more and more adversarial examples until for 0.3, we have the flat line. We have 0 accuracy because if I take any point from the training set and I move it to 0.3, then it's misclassified. Of course, if you look at this image, this is not representative of the training set, remember. The training set might not have points in the center of this stuff or anything. The loss is defined even outside of the training set, right? So there might be that if I take different points, that curve changes slightly. So what I do is increase the number of points and then check again and increase the number of steps, make sure that these attacks are all succeeding, etc. So this is the security evaluation. And it tells me that as long as I get perturbations, of course, these are adversarial perturbations. It's not random noise. It's the worst case. So if somebody wants to break my model, and I have this pretty model with these points that are from the Gaussian, etc., I know that they can perturb up to let's say 0.20 in epsilon, and I'm still fine. But then the model is not classifying correctly the points. Okay, and this is for knowing how robust is my model. Then what I can do is, for example, use some robust training techniques that, I don't know, they can reduce the influence of the gradients in the loss and try to move these boundaries a little more close to the data, not overfitting, but just robust training. Or another thing that I can do is just create something that detects the adversarial examples. So I can say if the samples are very close to the decision boundary, just rejects them. Don't classify them, okay? Well, now that we have concluded the Python notebook, there is the other coding part. So I can stop the Jupyter server. I also tried to upload the notebook on a collab, and it works fine as long as you add the line that I said. So this, I'm copying it in the chat, and you have to add it before the imports. I don't know if the chat is going to be broken by this command. No, okay. Okay, so requirements done, the notebook done. We can go on, and we are going to write a pipeline. So actually, I already wrote part of it, and it's available here. What I usually do with experiments is create a running script. So I have some arguments that I can pass as arguments to the program. When I run Python, name of the file, and then I can add keyword arguments. So for example, I can select the model, I can select the number of samples, etc. Okay, so I have an argument parser here. I don't know if you are familiar with this stuff. In Python, it's very commonly used. And it allows to do this, for example. So if I run, well, first of all, I have to go in the right directory. Then I can type Python. This is for passing a message to Python. So I'm calling the interpreter, and then I pass pipeline security without the .py, because this is going to be imported as a module. And this is a command that is usually encoded already in the argument parser. So if I define the parameters correctly, then I have this nice printout of the help module. It's broken again. Robustness, sorry. Let's see. This is strange. Ah, yes. I have still the other interpreter. I have to open another terminal. It's Conda stuff. Let me just. Okay, we have it. So, optional arguments. I can pass a model, and it's the ID of the model to use. Available models are, and then there's no model because we have to add them. Then there is this debug keyword that allows me to run the attack on a very small case. So what I usually do is have a debugging function that for which I can make sure that the attack is converging, everything is going fine. I can also visualize something. And then as soon as that works, I can extend to bigger experiments. Remember, always save time because you're gonna need it for writing papers or for doing other stuff. So be smart and always produce a small output that is representative of the final experiment. And then as soon as it works, then you can expand. But don't run the big experiments if you're not sure that they're gonna converge and do efficiently produced. Okay, and then the number of samples to use. I've put a check. So if we put a debug keyword, this parameter is ignored because I don't want to run the debug stuff in 100 examples. It's logging a lot of stuff. I don't want to see a lot of examples. I just need one to make sure everything is working. So what I can do is pass debug. Of course, it's gonna be broken because there is no model defined. Let's see. Exactly, list index out of error. And for this, I've created a few to-do items. I'm gonna go through them because I planned to leave you half an hour for solving this, but I figure maybe I can go through it very quickly also because the steps are all encoded. And then you can reproduce this later when you actually want to try it. But there's no time to waste here. No, it's not a waste. Anyways, if you have questions even later on, like when the lesson is over, feel free to send me an email or also a message on Teams in this account. The email, I think it's available in the repository, but it's just my name dot surname at unica.it. So very easy to remember, but it's easier if you write me on Teams, really. So I skipped a line here. So first of all, imports. We can forget about them for now. Actually, there is a script that is imported from another file, and I'm going to open it quickly later. Here it says, take two models from the Robust Bench library. Let's check out the Robust Bench library. It's on GitHub, also hosted in this website. And this is a library where one can create their models and then upload them in this site. And all the attacks are run automatically. And then the robust accuracy is posted. Okay? Be aware that instead of running the complete security evaluation, this is computing only a point of the security evaluation. So I fix, for example, epsilon to 0.5, and then I compute the robust accuracy at that value. And then we compare all models in that single value. Okay, so a slice of the plot that I showed you before. In this case, for example, we have for the Cypher 10 dataset, that is the one that has 10 classes that are RGB images, and it's one of the most used ones. Besides MNIST, that is the one with the digits that you'll probably know already. If you're here, I mean, you've seen it. So we have a perturbation model. As you see, it is L infinity. So you remember the box that I said before. So for each feature, we can perturb up to 8 divided by 255 because the images are defined in 0 to 55. Okay, so for each pixel and color, I can change up to 8 values. Sorry, 8 points in that feature, but for each feature. And here there is a list of models also with the link to the papers. So if I want to check out this one, I just go and see who is the author, everything. So there is the standard accuracy. That is the accuracy without perturbation, because we still want our model to perform well on random, on the dataset images. And then there is auto-attack robust accuracy. Auto-attack is the attack that is run for testing the robustness evaluation. It's something that it's slightly more complicated than PGD, but it takes care of automatically tuning the step size and everything we need for computing the attacks. So with minimal hyperparameter search, then you can run the security evaluation on that. Best known robust accuracy is the robust accuracy published in the paper. Because I can publish a paper and say my model is robust to 8/255, but it might be a lie. I might have configured my attack wrong or anything. So here they show the robust accuracy and the robust accuracy that was declared. Sometimes one of them is bigger than the other. The important thing is that it's not too big, okay? And the leaderboard can actually sorted for having the most robust accuracy tested here or the declared one. In this case, I think they are the same. And also, well, the other informations are this. It's new. I've not seen this column, but it's probably because the model might be adding some randomness. And so maybe the auto attack is not that good. Or also it might be like this case, where the robust accuracy with auto attack is lower than the robust accuracy with that was published. Sorry, it's higher. So meaning that the attacks are not succeeding as well as they are in this one. Then the architecture, because it's deep neural networks and we want to know if the model is huge or small or it's fast, slow. And then the venue where the paper was published, because if we have, for example, paper on arXiv, well, they are not, they have not been accepted as at a conference yet, or maybe the authors did not decide to submit to a conference, but still they are open access, and then you can get them and try them. And if they beat everything in the benchmark, then they're still better than the others. Or I can also take one of the big conferences and show that one paper was published, but the robust accuracy declared was really not the one that we found, and then just prove the authors wrong in that. Okay, so I would say we select the models and then we take another small break. So you can also try and
Sorry, I have a question.
Sure.
But as robustness, are you meaning security?
Yes. So it's a okay. Sorry, I actually skipped it, but it's a robustness to the perturbations with a maximum L infinity norm of 8 divided by 255. So.
Okay, fine, thanks.
You're welcome. Okay. So this is expecting a list of names from the robust bench library. So if I go in there, actually in the repository, or also model zoo, probably it's fine. And I go here, Cypher10, because we're using Cypher10 dataset. Then I have all the models defined, but what I need is the key in this case. I think it's in the bottom. So here are unique keys that are defined inside a dictionary. And if I take these, I can load this model instantly in the library. I'm not taking random models here because some of them is very complicated, because if you want robustness, you have to trade off with something else. Either it's the accuracy, or it might also be the time of computing a sample. For example, I can have 10 different models, all in an array of models, and then I take the decision out of them and take the majority vote. But it requires a lot of time, a lot of memory, and then, yeah, it might be robust, but it's also unusable. So in this case, I suggested these two keywords, but you're free to test others. So the standard model is a standard training model. So no robustness here, no particular mechanism for improving robustness. So it should be pretty much breakable with anything. And then this one is a model trained with adversarial examples. So one defense, it's simply to take the model, create a lot of adversarial examples, and then train another model that has the input data, the training data augmented with adversarial examples. So if I take a cat, make it into a panda, and then I label it as a cat, so it's adversarially perturbed, but I show it to the model and I say, this is still a cat. Even though there is a perturbation, this is still a cat. Then I can achieve some robustness. Of course, again, this has a cost. I have to create adversarial examples and show the model a lot of examples more, because also deep neural network are data hungry. So I would have to create a lot of examples. This model is already trained, so we don't have to make anything. We can download it, and they spent a lot of time creating adversarial examples and training it, so it's fine. It has I think it's outside of the benchmark now from the list that I showed you, because it's a pretty old model. By old, I'm saying 2019. It's not that old, but it's been overpassed. And now if I run the help script, I should see the two models that I've put. Okay, I have standard. So if I put a keyword model 0, and then debug, it's going to, well, it's going to break in some other part because there is still a to do to fix. But I think we can run it. So it's downloading the model automatically and creating, I think, a folder in here. So I'm just running it. So during the break, it downloads the models, at least one of them. Now let's take another 10-minute break. After the break, I'll show you, well, first of all, the logging part that is very interesting when you're running long computational time experiments. Okay, it has broken, but it's I know why it is. Well, preparing data, preparing model, preparing the attack, and then matching everything and running, and then achieving what we want to achieve. So perturb the examples and have some logging stuff saved. And of course, the results. And this is where it broke. There is no attack defined, because the other to-do item was to create an attack. We will see that in 10 minutes. In the meanwhile, if you have some time, you can check the script and analyze what is happening inside. But I'm going through it very soon. So 10-minute break. See you again in 10 minutes. And I'm still here for answering questions. Okay, final part. You ready? So in the meanwhile, sorry, my webcam is going away. In the meanwhile, I found an error in the key here. It was written as robustness net. It's actually only robustness. I think I took the name of the model instead of the key of the dictionary. Anyways, the keys of the dictionary are the ones that matter, and they are I think there is also a smarter way to find them. I think it's in model info. Okay, then we have different perturbation norms, perturbation models, L infinity. Okay, and then I have all the keys. So if I want the standard, this is the key. If I want angstrom robustness, it's this. So if I go here, there is the link from where the model was downloaded. Of course, this is all based on PyTorch, so it's very easy to load the models and run them with a framework because they all have the same interface. I do pytorch.load of the thing, and it's loaded. Then there is the reference to the paper. This additional data column is whether or not it was the data was augmented with other stuff. Number of forward passes is an information that, as I said, it's related to the computational time. If I have a high number of forward passes, 10, means that it takes 10 times a model that has one. Because sometimes just the models are many, or maybe there is a loop that passes through the forward a few times. So, because maybe there is randomness also in the model, and then it computes a statistics. So this is an indication that it's pretty useful. Dataset, etc. Okay, the architecture, the perturbation bound, and the information about the accuracy. But what we need is actually the name of the file. So I can also take another one and paste it there. But I'll keep those two because I know they take a small time for computing. Actually, this one, the trade-off is all in the training. If we create the adversarial examples in the training and we leave the architecture as it is, we are not having a cost when I'm using the model. It's only the cost is the added cost is only when training, because the forward takes the same time if I have the weights set to different values. So what is actually learning, it's changing the decision boundary, but the computational time of the model remains the same. Okay, then, as I said, this is very useful, and I suggest if you run experiments of any kind, even not machine learning ones, always have something like that, where you can change the parameters and have everything set. Now, I said before that we are not using a Python notebook for this. The reason is because maybe some library, this is something I struggled with a lot once, because some library imports, for example, I can import the model as model. Then that is kept in memory. And if I import another stuff and I call it model again, it's impossible to debug. So it's easier to stick to scripts in this case. Also, if the same Python notebook or script is used for many models, that's the same problem. So if I import two models and I create a loop inside the script, there is a risk of collision with the imports. So what I do when I when I'm using external stuff that I don't know how it imports stuff, I just make it a parameter of the script, so I can create a bash script and run all the commands that I need. So if I create new file, run all, no, sorry, it should be a bash file. So .sh. I can write Python. Remember that I'm running it from here, so I should go. No, actually, it's inside the src, maybe. -m, and just copy and paste what I have here. Okay. Then I can run lots of them. I just copy the line, put model 0. Maybe instead of the bug, I put the number of samples. And we're going to use it later, okay? So for now, just keep in mind that it's very useful to have parametric definition of the scripts. And also, you can create for loops outside. You can create a for loop in Bash. Let's go back to the script. So this parses the arguments that are recognized as keys and values from Python. So if I want the model ID, I just do args.model, and it's an attribute of that class, of that object, and then I retrieve the model ID. Then here we have the logger, and I'm using here a logger, a file handler. So the file is going to be named process log, and this is the format that I want. I want the time and the message. So if I open progress log, I have all the log information of what happened. I didn't print the errors here. I mean, I'm not redirecting the error, but it's possible. For now, I think I just put these for knowing the time it takes for computing an evaluation. Of course, we can delete it, but if I write more, it's going to append everything below. Okay, and this is standard logging. Then we have this debug keyword that, first of all, if the debug keyword is set, the number of samples would be ignored. Actually, I don't remember. In fact, it should be false by default. It's just when I was trying the script, I put it to true because I didn't want to write everything every time debug, but it should be false by default, meaning that if I add this keyword, it's going to run in debug. Otherwise, I don't want it in debug. Okay, and if the bug is set, then the number of samples is forced to 1. Prepare data. Now we are loading the Cypher dataset with a SecML library. And this is the image, as I said, but it's just made in a way that they are vectors. So if I take an image, I just ravel the array, and then I append also the 3 different colors. And it's still the representation of the image. It's just a different shape. And then here I'm taking a number of samples that I define from outside because I want to define it in the command line. And this is pre-processing for this data set, just because by standard, the images are saved in integer values. But then in machine learning, everything is usually set to 0 and 1. So if I divide every feature by 255, it's going, first of all, to become a floating point number, and also to become a floating point number between 0 and 1. This is just division. And also remember that here in the RobustBench website, the model, the attack model, was defined as 8 divided by 255. That is still, again, divided by 255. So I can set this as the epsilon constraint. So prepare model takes the model name as input and loads the model with a function stolen from the RobustBench library. This creates a folder, you can see it here, that has all the structure for loading the models and caching them, so I don't have to download them again, unless I want to force it. Okay. Then the core of the evaluation, prepare the attack. Here it says instantiate the PGD attack with the L-infinity threat model. So we have to use the class that is already imported. So before we use the L2, now we use the L-infinity, so the box. And sorry, let's open the class so we can have a look at it. So it's inheriting from another class. And this is what it takes as input. I think in the tutorial I said, okay, 10 steps, leaving all the parameters are as defaults, but I should find the keyword for the steps and for epsilon. So it's so epsilon, s with s, and steps. Now here in the tutorial, you should go to robust bench and find out what is the L-infinity bound that we use. In this case, it's 8 divided by 255, so we can write it down. Okay, and then with steps, there is still some required parameter, and it's the classifier. It is not set. Then what are the other parameters? Y target is the target label. So if I want a targeted attack, I can put a number there. For example, I want it misclassified as the class 2, and then it runs a targeted attack. Lower bound and upper bound, we can leave them as they are because we already set that, the bounds in 0, 1. These are the step sizes. We can define it relative to epsilon or absolute value. Okay, so if I put 0.1, it says I have an epsilon of 8 divided by 255. The relative step size, if I set it to 1/10, it's going to be 0.8 divided by 255. And then random start, again, starts the attack from a different point inside the epsilon region around the original point. So we have to pass the classifier here. And the classifier is passed as the input. Oh, actually, also epsilon is passed. Oh, I already set it. Okay, never mind. Okay, so it's going to pass the classifier and the epsilon. Prepare model, prepare data, then take X and Y. And the prepare data is taking one single sample for now because we're running the debug script. And it's computed the run debug. Let's open it up. So run debug, again, takes classifier, attack, and samples, and runs the attack on a single sample. Here, it's running the attack. Then we have some visualization stuff that is going to visualize the original image, the perturbed image, and the noise that we are adding. Amplified, of course, because it's very, very small. 8 divided by 255 it's imperceptible. I mean, on colored images, it's usually imperceptible. It might be a little big, actually, for this case, because it's a very small image. So it's, let's see. Then we visualize the loss of the attack. Again, this is going to be the cross-entropy loss of the model. Then we have perturbation size, because I want to check if the attack is actually moving. If the loss is flat, completely flat, I can put as many steps as I want, but the attack is not moving, okay? Or, for example, if I have a step size that is too small, I never reach the outside part of the epsilon constraint. I just stay close to the original point. So that's why I want to plot also the perturbation size. And then the logits of our classes, and this is the most interesting information because I'm going to see the outputs of the model and how they change as I increase the number of steps. So at every steps, it's taking the classification outputs. No, actually the scores. So it's a continuous change along the attack. And at some point, I will see the class score for the original label and the class score for the target label or for another class. They swap because I'm reaching the other region. Okay, so I've set everything. And then we are going to talk later about the other part, that is the actual experiment. So if I run an experiment in debug mode, let's run it in the non-robust model. So the 0, I set the standard as 0. Here, it's the index 0. So it's logging. It's saying that the samples will be ignored because I'm going to use only one of the points. I set 10 steps. Of course, these images are a little more complicated than the usual, than the previous dataset. So they take a little time to actually also to only to predict, but then we are predicting, computing the gradients, predicting, computing the gradients for 10 times, and also logging everything. So this is an airplane. I have the original label here, and the perturbed image, actually it's not visible. I don't think there is much difference. I mean, I wouldn't, if I only have these without the reference image, I wouldn't care that this image is perturbed. But it's classified as a frog, while it is clearly an airplane. And it's very far from a frog. This is the amplified perturbation. As I said, it's very, very dense. Every pixel is perturbed. If you want to try, you can also put an L1 attack, and it should become more sparse. Okay, and this is it for the example that we want to inspect. The attacker loss. In this case, we are decreasing the loss because the attack is defined with the negative sign. Doesn't matter the sign. The important thing is that we know if we want to increase or decrease it, okay? Because the optimization problem is defined, and then we have to run gradient descent. Then everything is set. It's just a matter of flipping signs and knowing where to go. Okay, so the loss is decreasing, and I see that with 10 steps, it kind of goes down, but probably if I put 11, 12, or 100, it could still go down. In this case, it doesn't matter because the logits are already flipped. But for example, in the other model, it might be too little. Perturbation size, this is a lot of perturbation size. Okay, there was a point that I was not seeing. So it already reaches almost, I think we are starting from the second point, because this is already 0.31, that is almost 8 divided by 255. Anyways, what we want to see is that we reach almost, or at least we don't have 0 as the distance. We want to have some distance from the original point, because I've set a region that is pretty big and I want to explore it all. So if I don't move, because it might happen that the attack actually goes down again, but at least I've explored that part of the region. Okay, and then, as I said, the very interesting information is the scores. So this was the score of the airplane class at the beginning of the attack. As I run the iterations, so 0 up to 9. So actually, there is that problem that the first point is not safe. That's the reason why we are seeing this. But it goes from 15. That is, okay, it's not a probability because it's not rescaled, but usually what we do is apply a function that puts all the scores between, they have to sum up to 1, and then there is appropriate functions to do so. But what it matters here is that in the end, when I'm classifying, I'm taking the highest score. So in this case, the highest score is airplane. I perturb it a little again and again. And at some point, it flips. It goes in the other class that was the frog class. You see, this is what's happening with adversarial examples. I'm moving slightly until 2 scores are flipped. The top score is flipped with another class. If I would select another class, for example, the green one, the bird, I would see this score go up. And maybe it would take more steps and more distance. But this is the difference between the two attacks, right? If I select a class, I have to struggle more, but then I reach that class. Instead, if I select any class, then probably the closest score is going to go up. So the score that was higher, because it's the closest class. Okay, and this is, once we know that this attack works, we can create, actually, we can also run the script. Let's run it for 4 samples because I don't want too much computational stress for the 2 models. Oh, right. First of all, let's explain what's happening. If I go here, there is a for loop. For every sample, we are selecting the sample, predicting the label, also logging some info because it doesn't hurt to do so. Run the attack, debug again with some info. Here I put debug, so if I set the login level to debug, I will see this. Otherwise, the script will just avoid to write these in the logging file. I don't remember what level I set here, but we will see. And then I'm creating a pandas data frame that is a very nice way to save information in Python because it keeps a table. So in this case, I'm appending a row in that table. And I'm saving it in a CSV report, so I can also open it and inspect it. Also, I'm creating the directory and saving the file. Also, in this case, be aware that if you don't put these and you don't have the results keyword, if you put, for example, 1,000 samples, then you come back and you read in the output, you're gonna read, there is no directory to save, so I'm not gonna save. So always try things in a small set and then increase it. So if I run this, okay, it's going. So, and you see, I see here that it's evaluating the first point of 4 points. So I also have information on how long it is taking to create the samples and what is the original label, predicted, and predicted after attack. This is not the robust model, so I'm expecting everything to be broken. Yes, okay. And then automatically the other script is going. If I open the results folder, that it's not shown now, okay. I have a CSV file and I can open that. And you see I have, well, the first row is usually the ID. So we don't care about that row. It's just the ID of the sample. Then we have predicted is a 2. Sorry, the original label is a 2. The predicted is a 2. And then I have the adversarial prediction is 4. Okay. This is, of course, for the perturbation model that I've set, etc. I'm not saving all the security evaluation curve. It's just one value for each of the points. Also, I think the other evaluation is completed, but I don't see the results yet. Here it is. You see this model is more robust because I have the first sample already. It's not changing labels. Maybe I can increase the font. Basically, all the labels are staying the same. Okay, this is a rather robust model, but it's also that I'm taking only 10 steps, and this model has, I mean, you can find adversarial examples, but you have to search for them a lot. Okay, then I have the results saved. Also, it's useful sometimes to store also the results. So like, for example, I can save the perturbations and then have all of them stored in some place. They're going to be images in the end, and I can reuse them later. So if I want to, for example, test another model, I can also take those perturbations and test them on another model without computing anything more. That I just save everything. Okay, so also keep in mind what you want to save before running the experiments. And then we have this very small script. As you saw, I ran for only 4 points. It took a bit. I think it's 1 minute. Yeah, 57 seconds. But it's only a small experiment. But I don't want to, for example, if I put a typo here, I don't want to run the experiments again if I put a typo, if I have a typo in the code, or maybe this mean doesn't work. I just want everything saved, so I have a reading results script that is compact and very small, but I just run it. It takes all the things that are stored in the results directory and produces an output. The output is going to be the model name, and then the standard accuracy. So if the original label is equal to the predicted label, and the other one is if the original label is equal to the adversarial label. So if I run this, I have the output. I cannot increase this. Oh, yes. So, and this is the reporting that I have from the experiments. So I hope everything is clear about creating a pipeline for the experiments and also creating experiments with the adversarial libraries. I mean, you can also change libraries and run the attacks in different ways. I would say the advantage of using SecML is exactly the debug part, where I can show all the things that are not available in standard attack. I would have to go inside the library, write my own code there, and change, store something. It is very complicated. So it's easier actually to use a library that already encodes that, but it's possible to do also the same thing with other libraries, or maybe just if you are only interested in running attacks, then you can run them from the other libraries. Now let me see if there is other things that I want to show you. If you have questions, of course, you can ask them. So the first thing that we can see is this paper that I personally worked on, and also the professor worked on, and also other students and other co-authors from the same lab. And so this is a work about understanding what are the failures in adversarial examples. So the thing that I showed you, those plots with the loss, with the scores of the model, etc., we developed them within this paper to understand automatically why an adversarial attack is failing. Okay, and this is something very interesting. Just to know that it's not over. There is still space to fix and to improve adversarial robustness evaluations. And in this paper, we actually define the attack algorithms in a way that they can easily be all put inside this algorithm here. And then we also show what can fail. I can show you this figure maybe. For example, the implementation problem that I said, it's this one. So the attack is running, and then at some point it's adversarial, but then it goes away. And the attack returns only the failed attack, okay? And instead, this attack was successful. So why should I compute all the stuff from this attack here and then have a failure if I found the point? It's just I didn't remember. So this is a paper that explores this kind of stuff and tries to understand what is the actual help that we can provide a developer if they want to evaluate their defense. And another thing about pipelines, it's a part of a project that I worked on. And this project performs a security evaluation. And there is a pipeline that is very similar to the one that I showed you. So you have a lot of APIs that allows you to define what you want to evaluate. So you pass in the path to a model, the path to a data set, and then you say it's a classification model. I want to test evasion attacks with this perturbation model. And this creates all the report for you, and you can finally, I mean, there's a lot of information in the README. Here is an example of queries that I can send. Too big. I pass all the information to this thing. This thing automatically instantiates all it needs to create the evaluation. Also provides some information. There is a queue for the jobs. So I can send more tasks, and it puts them in a queue, and they are sorted in a nice way, and they are going to be fetched one by one. They produce the results, and then they put back the information, and I can retrieve it. Okay, and it produces a report like, for example, this one. This is for a audio classification task. So there is a waveform that is transformed into an image, and I perturb that image. And then the image is classified into a set of keywords, okay? Anyways, the important thing here is that I'm perturbing images and creating exactly the security evaluation plot that I showed you. And also, since I wanted some debug information, I have the visualization of these are not meaningful for us. These are images of a spectrogram, so a transformed audio inside frequency and everything. So it's a different representation, but I can still visualize it and see if they are applying some perturbation. For the first case, epsilon is equal to 0, so I have 0 perturbations. And the scores, they say it's the keyword for left. I don't know, it's very small to read, but here are the keywords that it's recognizing. And these are different classes, actually. They are like silence and keywords that are not included in the dataset. Anyway, there is a set of keywords, and this word is a left. Then if I increase the perturbation slightly, it becomes more and more. Actually, the green ones are the original scores, and the red ones are the ones in the current epsilon model. So in the end, I think I have a misclassification. Yes. So it's recognized as on, keyword on here. All the other scores have gone down. Okay, so it's very interesting to have these kind of pipelines where you isolate what is the things that are changing, the things that are fixed, and then save everything in easy to read reports. And this is also included in our website. I mean, the same pipeline is also included in the website that you already probably saw. I think the demo, well, I have to search for the link, sorry. Anyway, you can encode everything into a website. So you have a queue, and then the user sent request, the request is processed, and then all the information is stored and showed to the user later. And that is easy to do if you have a very well organized pipeline that you can exploit for that. So I can actually send the link to this if you're interested. It's part of a European project that recently concluded. But this is an example of what you can achieve once you have a well-structured model to use for running the security evaluations. I'm just checking if I showed you all the tabs that I have opened. Okay. So, as a conclusion, if you have questions, either write them to me. This is my email address. And also try to play with the different things that I showed you if you want, or if you need for some project that you have. And I will try and understand what was the problem with the install libraries that I had. But probably it's just a matter of conflicting versions with Python and the library. So I will check that. We're also planning to upgrade the library soon. So if it's broken, it's gonna work. But I know that in the Google Colab, actually it works. So if you want to try the Python script, the Python notebook, I'm sure it works. For the local version, if it doesn't work yet, I'll try to debug it, but please send me emails with the information that, like the debugging information, and then I can provide you feedback. Or also you can open an issue in the repository. So you go to the GitHub page. No, actually the github.com repository. And you open an issue here. New issue, and you write everything, okay? That's because it's still an ongoing process, and we have to fix it if it's broken, so let us know. And also, it's very useful if you want to develop something. We can also let you develop something in the library. It's an open source project, and it's open to contributions, so feel free to send your requests, or send us an email, and we can help you with finding the correct starting input point for working on the library. Okay, I think that's it for today. I'm stopping the recording if I find the button. Okay.